Hi, and welcome to Does Anyone Really Need RAC? First of all, who am I, for those that don't already know me? I'm Karen Jex. I live in a small village in the French Alps with my family and our rescue dog Belle. I love cycling, mountain biking and skiing. I started out my career as an Oracle 7 DBA and became an Oracle 12 certified DBA. I spoke at several UK Oracle user group meetings and conferences and have now spoken at a couple of Postgres conferences. I started working with Postgres databases a few years ago after 20 years as an Oracle DBA. And I'm now a senior database consultant with Enterprise DB. One of the most common reasons we hear for not being able to migrate from Oracle to PostgreSQL is the fact that we absolutely, definitively must have RAC. Despite its cost and complexity, Oracle's RAC, or Real Application Clusters, to give it its full title, is widely used in response to a variety of performance, high availability, and/or scalability requirements, specifically write scalability. Postgres doesn't have a direct equivalent to RAC, and this seems to deter a lot of people. But does anyone really need it? In his 2003 white paper, You Probably Don't Need RAC, Morgan Norgaard states that if you have a system that needs to be up and running a few seconds after a crash, you probably need RAC. If you cannot buy a big enough system to deliver the CPU power and/or memory you crave, you probably need RAC. Otherwise, you probably don't need RAC. Alternatives will usually be cheaper, easier to manage, and quite sufficient. Norgaard didn't appear to have changed his mind in 2011, saying in an interview, RAC still has all the hallmarks of something people will want to buy. It increases complexity immensely, it's expensive, it requires specialists that are increasingly hard to find, there are always excellent alternatives, and it's pretty much perpetually unstable. In this talk, we'll look at whether or not Norgaard's original statement still holds true. We'll talk about what RAC is, what it does, why it's used, and the specific requirements that it fulfills. We'll then look at the various tools and methods, inbuilt, community, and proprietary, that are available in Postgres to fulfill these same requirements for the vast majority of applications. So what is RAC? RAC, or Real Application Clusters, was introduced in Oracle 9i in 2001 as an alternative to the classic single-instance database architecture, whereby one instance accesses one database. The RAC architecture allows several instances to be associated with a single database. Application connect to the database by specifying a service name and a scan IP, a virtual IP address for the entire cluster, rather than an individual host IP address and instance name. As an aside, from version 19c, RAC is only available in Enterprise Edition, not in Standard Edition. Some RAC terminology. Oracle Clusterware was introduced in Oracle 10G as the required cluster management infrastructure for Oracle. Prior to that, third-party clusterware was required. Oracle Clusterware is described by Oracle as a portable cluster management solution that binds multiple servers so they operate as a single system. An additional bit of terminology is the Oracle Grid infrastructure, which is composed of Oracle Clusterware and Oracle Automatic Storage Management, ASM. This enables you to create a clustered pool of storage to be used by any combination of non-cluster and Oracle RAC databases. So RAC isn't a single product, but rather an architecture. Step-by-step instructions for setting up a RAC cluster are provided in the 2-Day Plus Real Application Clusters guide, but the broad outline is to ensure that the server prerequisites are met, create the required OS users and groups and configure SSH so that they can communicate, configure a network between the servers, configure shared storage, install the grid infrastructure, Oracle Clusterware and Oracle ASM, configure the clusterware, install the Oracle RAC software, and create a database. What are the benefits of RAC? Oracle quotes high availability and scalability as the two main benefits of the RAC architecture. As they say, Oracle Real Application Clusters allow customers to run a single Oracle database across multiple servers in order to maximize availability and enable horizontal scalability while accessing shared storage. User sessions connecting to Oracle RAC instances can fail over and safely replay changes during outages without any changes to end user applications, hiding the impact of the outages from end users. The database spans multiple hardware systems and yet appears as a single unified database to the application. I believe that the claim that no application changes are required should come with caveats. In my experience, applications that work well with RAC have often been designed specifically to take advantage of the RAC architecture. An additional use case quoted by Oracle is to consolidate database environments. As they say, reduce infrastructure costs and the complexity of database environments by running more Oracle database instances on fewer servers without compromising isolation requirements. In my experience, and based on discussions with clients and colleagues, consolidation of database environments is not considered by most people as a use case for RAC. I'd argue that virtualization has a much larger role to play than RAC in consolidating multiple databases and applications onto fewer, larger servers. I'll therefore concentrate on high availability and scalability in this discussion. So let's look at high availability in RAC. RAC helps to minimize unplanned downtime. If there's a failure in one instance or server, access to the database is still available via the remaining instances. If correctly configured, connections that would have been serviced by the failed instance will be handled automatically by one of the surviving instances. Clients that are connected at the time of failure are notified. For this, fast application notification, FAN, needs to be configured. New connections are redirected to the remaining instances, and the outage is masked from the application and the client by replaying incomplete application requests. If correctly configured is a caveat here. As seen in the list of tasks in a previous slide, RAC installation and configuration is not a trivial task. It's not a plug and play one-size-fits-all type system. It's an architecture that needs to be designed and built to the specific requirements of a given application. For example, application services must be configured to ensure that new connections are redirected to the remaining instances following a failure. Services can be created on all of the nodes or just on certain nodes. They can also be configured with a set of preferred and allowed nodes to increase the options available in case of failure of a node. The application will specify the scan IP and a service name in order to connect to the database, rather than specifying a specific instance on a specific host. So a connection to service 1 here could be routed to any of the 3 nodes. If node 1 becomes unavailable, nodes 2 and 3 can still service connection requests for service 1. Node 2 can still service requests for service 2, and node 3 can still service requests for service 3. What RAC doesn't protect us from is disk failure. A failure at the storage level in this example would still cause unplanned downtime and data loss. It's therefore necessary to eliminate the single point of failure at the storage level. This is generally achieved through a combination of a robust tested database backup and restore policy and either physical or logical replica databases. Oracle recognizes this and tells users that tight integration with Oracle Active Data Guard and Oracle Golden Gate enables IT teams to maximize Oracle database availability and protection using proven Oracle maximum availability architecture best practices. Oracle Active Data Guard provides physical replication, whereas Golden Gate provides logical replication. RAC can also help to minimize downtime for planned maintenance, as it can be used to implement rolling upgrades and patching on a server-by-server basis. How does RAC provide scalability? Instances can be added to the cluster without application changes if and when additional resources are required. Resources are distributed amongst the various nodes in the cluster. The RAC Administration and Deployment Guide says that the combined processing power of the multiple servers can provide greater throughput and Oracle RAC scalability than is available from a single server. Though I have seen benchmark tests that suggest that this isn't always the case, so as always, testing is essential. Why we absolutely must use RAC. Many Oracle users are resistant to the idea of letting go of RAC, and I can understand that. I spent 20 years plus as an Oracle DBA, and I loved RAC. I loved the fact that if we lost an instance, or even two, the application could keep running without interruption. And we needed that reassurance because instances did go down on a regular basis. Until I started working with Postgres, I didn't really stop to think about that. Of course, we should plan for the situation where an instance or server fails and ensure that it causes little or no downtime, but we shouldn't expect it to be a normal part of day-to-day operations. I even loved the complexity of RAC, but possibly more from an academic point of view than a professional one. When looking at the possibility of migrating from Oracle to Postgres, and sometimes whilst explaining to us why it just isn't possible to move a certain application away from RAC, clients tell us, we need 0 downtime, we need 5 nines availability or 6 nines, we need 100% write availability, we need read scalability, we need write scalability, we have thousands or hundreds of thousands of TPS per node. We don't want a single point of failure. We don't want multiple copies of the data. We need thousands of concurrent connections. Most of these are genuine requirements, but not necessarily reasons not to consider alternatives to RAC. They generally fall into the high availability and scalability categories. We'll have a look at some of them in more detail, see where any limitations of Postgres might be, and which methods and tools are available to respond to users' requirements. I think it's important to say that a true guarantee of 0 downtime, 100% availability just isn't possible. We can plan for any number of failures, but there could still be a situation in which, due to unforeseen circumstances, meteor strike affecting both of our data sites, we encounter a situation where we either lose certain data or can't recover immediately from the failure. Just like a single standalone Oracle instance, or a single standalone instance of any database for that matter, a single standalone Postgres instance won't provide high availability and scalability. There are some limitations. In terms of availability, because there's a single database instance on a single server accessing a single set of database files, failure or unavailability of any one of those components will cause the database to be unavailable. In terms of scalability, it's generally recommended to configure Postgres to allow only a relatively small number of concurrent connections. The default value for max connections, the maximum number of concurrent connections that may be established to the database, is 100. And conventional wisdom suggests that it shouldn't be set higher than around 300 to 500 in most cases. Because of the PostgreSQL one process per connection model, there are non-negligible OS overheads associated with opening a large number of concurrent connections, even if the majority of those connections are mostly idle. This can cause significant performance degradation. In his article, Analyzing the Limits of Connection Scalability in Postgres, Postgres committer Andres Freund explains in detail the limiting factors, specifically memory usage, snapshot scalability, and connection model. He identifies snapshot scalability as a significant but improvable bottleneck. The graph on this slide is from his article, showing how much throughput decreases as the number of mostly idle connections increases. There's some great news to come out of this. In his subsequent post, Improving Postgres Connection Scalability Snapshots, Andres describes the improvements that he recently contributed to Postgres 14 to be released in Q3 of 2021, significantly reducing the identified snapshot scalability bottleneck. The results of his benchmark tests, as shown in the graph that I've taken from his post, suggest that even with up to 10,000 idle connections, throughput remains stable. It's often quoted that Oracle performs better than Postgres, but it's difficult to find benchmark figures that compare like with like. In any case, various different benchmarks suggest that a single PostgreSQL node can handle some tens of thousands of transactions per second for certain workloads. This is sufficient for the vast majority of applications, but there are, of course, applications out there that need to process hundreds of thousands or even millions of potentially complex transactions per second. A single node of either PostgreSQL or any database is unlikely to provide the level of throughput required for this type of application. So what are the alternatives to RAC that are available to us in Postgres? Let's look at the methods and tools available to respond to each of these requirements. The open source nature of Postgres means that, in addition to inbuilt options, there are also many third-party tools available, both open source and proprietary. But first of all, a disclaimer. I haven't used some of the tools that I talk about here, nor are they all necessarily endorsed by or supported by EDB. I mention them purely to discuss the fact that they exist and that they provide certain useful functionality. As always, rigorous testing is required before implementing anything in a production environment, and if in doubt, you could always engage an EDB consultant for help. Firstly, high availability. One of the main methods for ensuring continuous availability of any system is to avoid single points of failure. In the case of a database system, this includes both the database itself, the data files, and the database instance, the memory and processes that access the database. In order to eliminate this single point of failure, Postgres includes inbuilt options that allow replication of a primary database to one or more replica or standby databases. From our primary database, we can have physical replication, which is an all or nothing copy of the entire database that's kept up to date by continually applying changes to the standby database as they occur on the primary. This can be via log shipping or warm standby, whereby WAL is continuously archived from the primary and used by the standby for continuous recovery, or streaming replication, where changes are applied almost immediately on the standby database rather than waiting for a WAL file to be copied over and applied. We can have cascaded replication, where changes are replicated from one standby to another. The standbys can either be synchronous, where the primary waits for confirmation that the changes have been applied on the standby before committing the changes. In the case of primary database failure, we know that all committed changes have been applied to the standby, thereby providing some protection against data loss. The trade-off, of course, is a potential wait for writes if there's network latency, or if the standby is unavailable for any reason. Or standbys can be asynchronous. The primary doesn't wait for confirmation that changes have been applied on the standby before committing the changes. If the primary server fails, however, some committed transactions may not yet have been applied on the standby server, causing data loss. The alternative to physical replication is logical replication, sometimes known as transactional replication. This allows changes to a subset of objects to be replicated rather than an entire database. Changes are replicated from a publisher database to a subscriber database. Of course, creating a copy of the database is only one step in creating a high availability solution. In case of failure of the primary database, the baton should be passed to one of the other databases, which will become the new primary, and application connections should be rerouted to this new primary database. Ideally, this will happen automatically, swiftly, and be transparent to the end users. There are many different tools available that allow us to configure high availability in Postgres, both open source and proprietary, such as EDB's Failover Manager, EFM, pgpool2, Patroni, Corosync, Pacemaker, PostgreSQL Automatic Failover, Stolon, repmgr, and pglookout. In general, high availability solutions have the following characteristics or functionality. A virtual IP or VIP that's allocated to the current primary database, monitoring of the current status of the databases in the cluster and of the replication, and a way to identify failure of the current primary database and take appropriate action, i.e. promote the new standby database to be promote the appropriate standby database to be the new primary, and avoid a split brain scenario by ensuring that the failed primary database can't be reintegrated into the cluster. I won't discuss all of the tools in detail, but I will briefly describe the way in which a couple of them work to give an idea of the functionality that they provide. Of course, I have to talk about EDB's Failover Manager, EFM. The EFM agent runs on each of the database nodes in the replication cluster and optionally on an additional witness node. EFM monitors the status of the databases and the replication, and it maintains a VIP that's assigned to the current primary database. In case of failure of the primary database, EFM will identify the most suitable standby based on the apply lag and the standby priority, release the VIP from the old primary, run any fencing scripts that have been defined, promote the identified standby to the role of primary, assign the VIP to the new primary, run any post-promotion scripts that have been defined, reconfigure existing standbys to replicate from the new primary, and prevent accidental restart of the failed primary database to avoid a split brain scenario. EFM can also be used to perform a manual switchover from one primary to another, allowing planned maintenance to be performed without downtime. Patroni, according to its documentation, is a template for you to create your own customized high availability solution using Python, and for maximum accessibility, a distributed configuration store like Zookeeper, etcd, Consul, or Kubernetes. They advise potential users that Patroni is called a template because it's far from being a one-size-fits-all or plug-and-play replication system. They go so far as to say that it will have its own caveats. Use wisely. Patroni uses PostgreSQL's native streaming replication, together with HA proxy, which allows connections to be routed to the current primary database. The various YAML files provided can be modified to change the configuration to suit your requirements. Corosync and Pacemaker is a stack that allows users to implement a high availability cluster. Pacemaker is a cluster resource manager. It detects and recovers from node failures by making use of the messaging and membership capabilities provided by your cluster infrastructure, in this case Corosync. Corosync provides cluster infrastructure functionality. It maintains the quorum information. This feature has been utilized by Pacemaker to provide a high availability solution. PostgreSQL Automatic Failover is a cluster resource agent that's based on the Corosync and Pacemaker stack. It provides the abstraction that allows Pacemaker to manage Postgres. Let's look at some of the options that provide scalability. Some of the methods that can provide scalability are connection pooling, read-only replicas to provide read scalability, multi-master replication, load balancing, and sharding. A connection pooler maintains a pool of connections to the database that can be reused by new connection requests. This can allow a relatively small number of database connections to service a large number of application connections. New application connections can be established and existing ones closed, but the pool of database connections remains constant. Fewer connections are created on the database and less time is taken establishing and closing connections than without a connection pooler. Examples of connection poolers are pgpool2, although this does more than just connection pooling, and pgbouncer. Read-only replicas sometimes known as hot standbys, can be used to provide read scalability. We don't want multiple copies of the data is sometimes used as an argument for not wanting to use replication in order to provide read scalability. I'd argue that it's actually desirable to have at least one additional copy of the database in order to provide high availability, as seen in previous sections, and to protect against data loss. In fact, RAC users will commonly use either Golden Gate or DataGuard to create a replica database for reporting and/or disaster recovery purposes. Multi-master replication, or bidirectional replication, can be used to provide write scalability. Multiple copies of the database exist in read-write mode. Changes made to any one of the databases will be replicated to the others. Certain applications will be better suited than others to this method of replication. Ideally, applications will be written in such a way that conflicts, where two nodes attempt to modify the same data at the same time, are avoided as much as possible. Geographically distributed databases, or databases that are majority inserts rather than updates, would potentially be good candidates. A multi-master replication solution needs to handle such conflicts if and when they do arise. An example of a tool that implements multi-master replication is bidirectional replication, BDR, from Second Quadrant, which is now part of EDB. A load balancer sits between the application and the database and routes client requests to the appropriate database instances in order to distribute the requests across the available resources. pgpool2 is an example of a tool that provides load balancing capabilities. Sharding, or horizontal partitioning of the database, is the practice of storing a subset of the data in a number of independent databases. The data could, for example, be split geographically per country or region. This makes sense where an application naturally accesses only a subset of the data in the database. For example, regional sales teams accessing data only for their own region. Management of any shared data, for example, reference tables, must be carefully considered. It may, for example, be necessary to replicate these across all of the databases. It may also sometimes be necessary to access the entire logical data set, for example, for reporting purposes, in which case mechanisms must be put in place to allow aggregation of the data in each of the databases. This could be done, for example, by logical replication to an aggregated reporting database, or via foreign data wrappers that access each of the databases. There are a number of tools that provide sharding for PostgreSQL, for example, the Citus extension to PostgreSQL and PostgreSQL XL. There's no one ideal, highly available, performant architecture. The architecture you design will depend on the requirements of the applications that will run against the database. You'll want to ask yourself questions such as, what workload does this architecture need to support? Is it for reporting or for OLTP? What's the ratio of reads to writes? How complex are the SQL statements? How many transactions per second are expected? Will the database be hosted on-premise or in the cloud? How large is the database, or how large will it grow to? What are the business requirements? What level of write availability is required? What level of read availability is required? What's the recovery point objective, RPO, or the maximum permitted data loss? What's the recovery time objective, RTO, i.e. the maximum permitted length of an outage? What are the uptime requirements? How many nines? Consider the different options that have been discussed, but keep things simple where possible. Imagine the admittedly rare scenario of an application with a workload of less than 100 transactions per second, tens of concurrent connections, and an expected database size of a few hundred gigabytes, where losing 24 hours worth of data is not an issue, and we can afford to wait several hours to be back up and running after a database failure. In this case, a complex solution involving multi-master replication, load balancing, and connection pooling would be unnecessarily complex and expensive. A standalone database with a daily, well-tested backup may well be considered sufficient. If, on the other hand, the database is several terabytes in size, there are hundreds or even thousands of concurrent connections, many thousands of TPS, an RPO and an RTO of seconds, a standalone database is clearly no longer sufficient, and specific methods and tools will need to be put in place to ensure that the architecture can deliver the level of performance and availability that's needed. Consider both unplanned downtime and planned maintenance. Replica databases, for example, can be used to implement rolling upgrades and patching on a server-by-server basis. Are there times when it might be difficult to migrate from RAC? There might. An application that's currently running on RAC may well have been designed from the ground up with that particular architecture in mind. It may be difficult, i.e. time-consuming and costly, to make the type of fundamental application changes that would enable it to adapt to certain other architectures. When considering a migration from RAC to Postgres, it's therefore essential to analyze the workload and the requirements of the application in detail in order to ensure that a suitable architecture is designed that will meet its needs. It will be necessary to weigh up the costs and risks associated with making the changes required to ensure that the migration is successful against the potential advantages and cost savings involved in moving to Postgres. So to go back to Norgaard's original conclusions and see whether or not they still seem to be true, if you have a system that needs to be up and running a few seconds after a crash, you probably need RAC. I don't think this is true any longer. With some of the tools that we've discussed, a system can be up and running a few seconds after a crash without requiring RAC. If you cannot buy a big enough system to deliver the CPU power and/or memory you crave, you probably need RAC. In fact, machines with enough memory and CPU to cope with even the most demanding of workloads are now readily available. Even if this was not the case, the different replication options available in Postgres mean that servers can be clustered to provide the resources required. If you need to cover your behind politically in your organization, you can choose to buy clusters, Oracle, RAC, and what have you, and then you can safely say, we've bought the most expensive equipment known to man. It cannot possibly be our fault if something goes wrong or the system goes down. This argument may still hold some weight in some organizations. I'll leave the last word to Norgaard, as I don't think I can say it any better. Otherwise, you probably don't need RAC. Alternatives will usually be cheaper, easier to manage, and quite sufficient. Thank you for listening.